Okay, now let us see what we call centripetal acceleration and centripetal force in this lesson. Okay, consider a particle moving with a uniform, not the word uniform, circular motion with a constant linear speed v. So we are going to say it is moving from A up to point B. So it's here at S having velocity A, and here it's having velocity B, as you can see there. So from here up here is the center, and this is the radius. So hope you can remember the idea of relative velocity, but I'm going to come back to that later. So from, when you are getting the angular displacement, we get a distance over the radius. So from here, so this is S over R. And so now my displacement is R of theta, meaning the distance from here up to here is going to be R times theta. Note, our acceleration is always given by changing the velocity over time. So you need the change in velocity over time. Okay, I'm going to come back to that later. Now, if I try to use the idea of relative velocity, it means that now I have to get a negative of this, and I keep this positive here. So, you see, if I maintain the distance, I mean the direction of this velocity b, and then I reverse the direction of this velocity at a, I'll be having the velocity of b relative to the velocity of a. And so this one is going to be equal to the change in the velocity. How? If you want to get a change in the velocity from here up to here, we shall get the velocity at b minus the velocity at a, which you can see is there. The change in the velocity is velocity at b minus velocity at a. And so this change in the velocity is equaling to the relative velocity of b relative to a, which you can see is that. That's why is that. Now, you note that the relative velocity is moving towards the center. You see, it's moving towards the center, as you can see there. Come back to that. And the angle between the velocities, vectors VA and VB is the theta. So if I try to do this, I think this one is going this side. This one, you see it's continuing that side, and then this one is going this side. So, but the angle between them is always going to be theta. So if this one is that side and this one is that side, angle between them is going to be always theta, as you can see. Or you can use this idea here. No problem. It's okay. Now, you know that our angular velocity is going to be the change in velocity over the velocity at A. But now we say, since V is constant, we say the constant linear velocity V, speed V, means that VA, VB is going to be the same. Now, the idea here with the circular motions, velocity is constant, but doesn't mean that acceleration is zero. Because it's moving with the constant velocity, but doesn't mean that acceleration is zero. Here, circular motion. So, where there's this, I call this, and I call small pi. So now my change in the velocity is going to be equal to the velocity times theta. Now, from here, you know that our acceleration is given by changing the velocity over t. This is from here, then over t. But now, I know from our velocity is always given by displacement over time. I want to remove that time. So my time is now, if I cross multiply and I interchange, this is what I have. But now I know that always displacement is equal to the radius times theta from here. And then you can see it there. So if I put it where this S, I put r theta, I have that. And then when I put in my this, then our t is now this from here. Then you see I will divide, then I will multiply. So it's that this will cancel. I'll be having this squared over r, and that's what we call the centripetal acceleration, because so this velocity is heading always directed towards the center. Since D is directed towards the center of what? Center of, then A is called the centripetal acceleration. That's it. Since I think you can see it from here clearly. If I bring it here, it's directed towards the center there. Okay, now look at from the first lesson, from the second lesson, and the first lesson, we saw that angular velocity is related to linear velocity in this way, so that linear velocity is the product of the angular velocity times the radius of the circular path. Now, from here, if I substitute this very put that from here, now it's this radius, 1 r, this r, is going to cancel with 1, and so our acceleration is going to be given by the angular velocity squared times the radius of the path. Since the object is accelerating, then there is a force that keeps it moving in a circular path according to Newton's second law of motion. Hope you remember those laws at the start. Now, this is how it's sort of like this, that the force is always equal to the mass times the acceleration, meaning, and always is in the direction of that acceleration. So, we have our acceleration now from here, and put it there, and see that now, this one is what we call now the centripetal force that is keeping that object in that circular motion, as you see. So, the force that is keeping this object moving in that, because it's that it's accelerating, but I think it's that I'm accelerating it at a uniform velocity, but it's accelerating. So that force that is keeping it in that motion like that is what we call the centripetal force, as we've seen there. So that's it, members. We are going to see now, we are almost close to examples in the next lesson. Before we are going to see the problem, how do we solve them, and then we'll see some simple examples, of course. See you in the next lesson. But please don't forget to subscribe to the channel.